Hi everyone, now let us look into our topic today, relations. What is actually relations? Basically, relations defined as the relationship between elements of two sets, A and B, where A is element of A and B is element of B. If R is a relation on the set S, that is R is subset of S times X, and Sy is element of R, we say that S is related to Y. Properties of relations includes reflexive, irreflexive, symmetric, antisymmetric, asymmetric, and transitive. The relation R on the set S is reflexive is for all S is element of S. S is element of R. For example, the relation R is considered reflexive as it contains each duplicated version of element in set S. A relation R on set A is irreflexive if all A is element of A, but AA is not element of R. For example, the relation R is considered irreflexive as no element in the relation consists of the same number. The relation R on the set S is symmetric is for all Sy is element of S. Sy element of R implies that Ys also element of R. For example, the relation R is considered symmetric because phi 6 exists, implies that 6 phi exists. A relation R on set A is antisymmetric if A and B is element of A, AB element of R, BA element of R, and A and B is the same. A relation R on set A is asymmetric if A and B is element of A, AB is element of R, but BA is not element of R. The relation R on the set S is transitive is for all SYZ is element of S. Sy element of R, YZ element of R implies that SZ also element of R. For example, the relation R is considered transitive as we have 4 5 as AB, 5 6 as BC, and 4 6 as AC.
Now let's look at combining relations. Relations are sets, which means they can be applied to set operations. If R1, R2 is a subset of A times B, we can define it as R1 union R2 is a subset of A times B, and R1 intersect R2 is a subset of A times B. Now let's look at composite. Let's say R is a subset of A times B and S is a subset of B times C. Composite of R and S is written as S composite of R. Denoted that AC, AB is the element of R, BC is the element of S, A is the element of A, B is the element of B, and C is the element of C. To get a clearer picture, let's look at an example. Given DS are relations on A, 1, 2, 3, 4. Set D is parenthesis A, comma B, close parenthesis, only if B equals to 5 minus A. From this formula, we can get 5 minus 1, which is A, equals to 4, which is B. And it continues until we use as much numbers in relations A as we can. Next, it's given that set S is parenthesis A, comma B, close parenthesis, only if A is smaller than B. From this formula, we can put 1 as A and 2 as B, because B is bigger than A. We cannot put 1 as B because 1 is not bigger than 1. And it continues until we use as much numbers in the relations on A as we can. Question here is, what is S composite B? Well, if you look at set S and D with their formula, when you look at S, it's saying that A is smaller than B. But originally, S is mapping from A to B. But right now, for the composite, instead of mapping from A, we're mapping from D. And over here, it says that D is 5 minus A. So instead of mapping from A, you're mapping from 5 minus A. So we get the formula 5 minus A is smaller than B. Now you have the formula for set S composite D, which is parenthesis A, comma B, close parenthesis only if B is bigger than 5 minus A. You can also rearrange it and get this formula. Using these formulas, you'll get the subset of set S composite D. Alright, now let us look at power relations. Given R is a relation on set A, the powers of R to the power of n, where n is equals to 1, 2, 3, and so on, are defined inductively, where R to the power of 1 is equals to R to the power of n plus 1 is equals to R to the power of n times R, or R to the power of n is equals to R times R continuously n times. Now let's look at the theorem. The relation R on set A is transitive if and only if R to the power of n is a subset of R for all positive integers n.
Moving on to how to represent a relation. There are two ways to represent a relation. Number 1, 0-1 matrices, and number 2, directed graph or called digraph. This is one of the ways, which is 0 matrices. Let's assume that R is a relation from A to B. R can be represented by 0 matrix MR to MIJ. The value of MIJ will be 1 if AB is the element of R, MIJ will be 0 if AB is not the element of R. Let's look at this example. Represent relation R21, 31, and 32 as a 0 matrix. For the AB that is in the relation of R, the MIJ will be 1, otherwise it will be 0. There are also certain patterns for each properties of relation. For example, relations on a set, which is P matrices. For reflexive relation, all diagonal elements will be 1s, and for symmetric relation, 1 will be paired with 1, and anti-symmetric relation, 1 will be paired with 0, or 0 will be paired with 1. Boolean operations can also be represented in 0-1 matrices. Boolean operations consist of two types. One is union of two relations, called Boolean or join, and the other one is intersection of two relations, Boolean and or meet. This is the example. Let's assume that this is the metric of MR, and this is the metric of MS. For the left side is the union of the two matrices, and the right side is the intersection of the two matrices. Now, let's see how to represent the opposite of two relations. Let's assume that relation A represented by matrix MA and relation B represented by matrix MB. So the opposite of BA is the Boolean product of MA and MB. Let's look at the example for better understanding. This is the example. For matrix representing R squared, where the matrix is R is given. The recipe for R squared is MR squared. Using diagram is the next way we can use to represent relation. Look at the board. Directed graph or digraph. It consists of a set of V which is vertices or nodes, a set of E which is edges, and for H it has two components which is initial vertex and terminal vertex. It also uses arrows to display from initial vertex to terminal vertex. This is the example. Display the digraph. A to B, A to D, B to B, B to D, C to A, C to B, D to B, and each of the form BB is called a loop. Representing relations using diagram. Any relation R on a set A can be represented with a digraph with A as its vertices and R plus AB element of R as its edges. Any digraph with vertices V and edges can be represented by a relation on V containing all the pairs in E.
Next is the relational database. An array relation. Let A1, A2, AN be sets. An array relation of this set is a subset of A1 cross A2 until AN. A1, A2, AN is the domains, while N is the degree. For example, let A1 be a set of names, A2 a set of addresses, and A3 a set of telephone numbers. Then a set of three tuples name, addresses, telephone numbers, such as this example is a ternary or ternary relation over A1, A2, and A3. Primary key. Primary key is the domain of an n-array relation whose values uniquely determine the n tuples. No two records can have the same value from the same primary key. For example, the primary key from 4 tuples with the fields student name, ID number, major and CGPA is student name and ID number. Composite key. The definition, combination of domains can also uniquely identify n tuples in an n-array relation. When the values of a set of domains determine an n tuples in a relation, the Cartesian product of these domains is called a composite key. For a relational database, a database consists of n tuples called records. Each of the n tuples is called a field. fields are entries to the n tuples. Operation on n array. First one is projection. Pi1, I2, Im maps the n tuple A1, A2, An to the m tuple Ai1, Ai2, Aim where m is less or same as n. Second one is join, where it is to combine two tables into one if they share some identical fields. Now we move on to equivalence relation. A relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. It is to relate objects that are similar in some way. Two elements that are related by an equivalence relation are called equivalent. Equivalence classes. Partition. Let A be a set and A1, A2, An be its non-empty subset. The subset from a partition P of A if the union of the subset in P is equal to A, the partition P does not contain the empty set, and the intersection of any distinct subset in P is empty.